Let's jump right into this explainer. Today, we're demystifying the absolute brain behind industrial automation, the PID Controller. We'll be taking a visual journey from total chaos to perfect, smooth control. We're going to break down exactly how incredibly complex physical systems, like think regulating heat transport in nuclear reactors, or even just maintaining basic water levels in a boiler, how they manage to strike that perfect, continuous balance.
Now, it's pretty fascinating to see how this quest for automated control actually evolved over the centuries. I mean, we started way back in the 17th century with Huygens' mechanical centrifugal governor. Fast forward, and we see this massive leap in 1911 when Elmer Sperry introduced a practical PID-type controller for automatic ship steering. Then, Nicholas Minorski mathematically formulated the control law in 1922. And finally, in 1942, we hit the rigorous Ziegler-Nichols tuning methods. Honestly, it's the exact same foundational math that plant operators rely on to this very day.
So here's our roadmap for this explainer. 1. The basics of process control. 2. The simplest approach, on-off control. 3. Proportional control and offset. 4. Integral action eliminating that offset. 5. Derivative action anticipating change. And 6. Tuning your PID controller. Section 1. The basics of process control. Understanding set points and error. All right, the absolutely crucial point here is that control action only happens when there's an error. And what's an error? It's just the simple difference between what we want, which is our set point, and what we actually have right now, our measured quantity. In a closed-loop feedback system like this, an error literally has to occur before any corrective action is taken. So it's inherently a retrospective system. The system just continuously measures that error gap and fires off a signal to counteract it, essentially keeping the problem from compounding into a bigger mess. Section 2. The simplest approach. On-off. The binary world of control. Okay, check out this basic tank setup. We've got an electrically operated solenoid valve managing the water inflow. When the water level hits a very specific low point, which we'll call L1, a differential pressure switch just blasts that solenoid valve 100% open. And then, at the high point, L2, it slams it 100% shut. It is a completely binary all-or-nothing approach. No in-between. But this brilliantly illustrates the big flaw with a binary system like that. You can never, ever maintain the exact set point, because that valve is only ever fully open or completely closed. You just get this sluggish, constant sinusoidal wave. It's just endlessly overshooting and undershooting the target. Actually, engineers intentionally build in a deadband. That's the gap between L1 and L2, specifically to prevent the valve from rapidly cycling back and forth and completely destroying itself. Now, this aggressive, swinging cycling, it's perfectly fine for a slow, sluggish system, like a large electric water heater where the thermal mass kind of absorbs those shocks. But for precise industrial manufacturing, no way. We have to ask ourselves, how do we stop the bouncing? If on-off control causes constant oscillation, how in the world do we achieve a finer, continuous adjustment? Section 3, Proportional Control and Offset. A step towards finer adjustment. Well, by replacing that clunky binary switch with a pneumatic level transmitter and a control valve, we step up our game. We can now provide a continuous adjustment that's directly proportional to the size of the error. Think about it. If the error is small, the valve opens just a little bit. If the error is huge, it opens up a lot. Using a standard pneumatic output, say like 20 to 100 kilopascals, this controller is continuously modifying the flow based on the exact magnitude and the direction of our error. But if we look closer at the system response here, it reveals a pretty frustrating new problem. Yes, the system stabilizes, which is awesome, right? We finally lost that extreme sinusoidal wave. But it leaves behind this permanent gap just below our set point, which engineers call an offset. Because the proportional control signal only changes when the error is actively changing, after a disturbance, it'll eventually just find a new mass balance and stubbornly settle there. It stabilizes the error for sure, but it completely fails to actually eliminate it. So we've taken a huge step forward, but we've kind of hit a wall here. Proportional control stopped those crazy oscillations, sure, but if we need absolute pinpoint precision in our plant, how on earth do we force that offset gap entirely to zero? Section 4. Integral action eliminates offset, restoring the perfect balance. Let's see how this next piece builds on what we just did. This is the I in PID, integral action. You can think of it acting like the system's memory. It continuously adds up or integrates the error over time.
Notice how, as long as any offset exists, no matter how small, the integral controller just patiently and persistently ramps that control valve open further and further. It keeps pushing until that offset is completely crushed, bringing the system right back to our perfect set point.
You really do have to be careful here, though. While integral action is absolutely essential, it does introduce some additional lag. If your integral reset rate is set way too fast, or if some physical limitation prevents the error from correcting quickly enough, you run a huge risk of something called reset windup. This is a pretty dangerous condition, where the controller just continuously adds up that error and ends up maxing out your valves at either 0 or 100%. Ironically, this actually makes the system far less stable and causes massive physical wear and tear on your equipment.
So, okay, assuming we manage our windup properly, we now have a perfectly stable system sitting exactly at our desired set point. But reacting to past, accumulated errors is inherently a slow process. It really begs the question. We've eliminated the offset, sure, but can a controller actually anticipate an error before it gets worse? Like, can it effectively look into the future?
Section 5. Derivative action anticipates change, seeing into the future of the system.
This brings us to the D in PID. Notice how the derivative action provides this immediate, massive corrective spike the very second it senses a steep slope in the error. It doesn't actually care about the size of the error, it's looking entirely at the rate of change. By throwing a massive correction at a fast-moving error right out of the gate, it effectively anticipates the problem before it has a chance to grow, which greatly reduces your overall system lag. Now, a quick caveat. You definitely wouldn't want to use this on fast-acting processes like flow control, because even tiny little signal noises would cause erratic, crazy valve stroking. But for sluggish systems, it's an absolute game-changer for rapid recovery.
Section 6. Tuning your PID controller. Finding the perfect balance.
Now, having all three components is great, but they're useless if they aren't balanced. If you're an operator doing manual trial and error tuning, you're going to follow these 5 exact steps. First, you just zero out your integral and derivative actions entirely. Then you basically push the system to its breaking point by gradually cranking up your proportional gain until you hit sustained oscillation. Once the system is bouncing, you back off that P gain by about 30 to 50% just to stabilize it again. Then you patiently layer in your integral action, just enough to kill that offset. And finally, you add your derivative action to smooth out the overall stability.
But manual tuning definitely isn't the only way. For a more rigorous mathematical approach, you can use those famous Ziegler-Nichols formulas we mentioned right at the start. By using these formulas, you literally take the dead time, which is just the delay before your system actually reacts, along with the maximum reaction rate of your process, and you can calculate the exact numerical gains you need for your P, I, and D parameters. It takes out a lot of the guesswork.
When you're using the Ziegler-Nichols method, you really have a distinct choice in how to test. You can run an open-loop test, putting the controller in manual mode to safely observe the reaction curve. That carries a very low risk of oscillation. Or, on the flip side, you can run a closed-loop test, leaving the controller in auto mode and purposely pushing it right into sustained oscillation. Now, the closed-loop method is highly accurate for complex feedback systems for sure, but you have to keep in mind it carries a much higher risk of actually destabilizing your whole plant.
So let's summarize this whole complex journey we've been on. Proportional control gets us close by providing the muscle, but it stubbornly leaves an offset. Integral action comes in acting as the memory, making things perfect by patiently eliminating that steady-state error. Derivative action acts as the eyes, making the system incredibly fast by anticipating rapid changes. And finally, tuning makes it safe, serving as this essential masterclass to balance all of these amazingly powerful mathematical forces out in the real world.
Because real-world processes change so dynamically over time, many of these systems are going to require periodic retuning. So, we're going to leave you with this final thought to ponder about the whole future of automation and really the operators who control it all. As physical plants become increasingly complex, will manual tuning become this lost art, entirely replaced by auto-tuning algorithms? Or will the foundational math of PID always require that touch of human intuition to safely balance the equation? Thanks so much for exploring the fascinating mechanics of process control with us today on this explainer.